Okay, so we're gonna get started on chapter 2. First, section 2.1, talking about some early or history of some very short history of number theory. So I'm just gonna leave that for you. So I want to get started on section 2.2, and the title of this section is the division algorithm. All right, so these are the objectives that we're going to cover in this section. First, we're going to state and prove the division algorithm. Then we're going to look at some of the applications of division algorithm, a few applications, and more applications and more uses of the division algorithm we're going to actually see throughout the the course. Then we're going to give a definition of a binary relation on the set of integers. It's called divides. Okay? And then we're going to prove some properties of this relation. Then we're going to move into defining what we mean by the greatest common divisor of two integers. All right, and then we're going to give different characterization, different ways of defining basically the greatest common divisors of two integers. And then we're going to end by proving some properties of the greatest common divisor. All right, it's a very big list, but I hope every term actually in here you are familiar with. Have you seen it before? There's nothing really extraordinary or totally unknown. All right, so let me get started with the statement of the division algorithm. First, the division algorithm is actually gives the outcome of dividing an integer by a positive integer. All right? So this is really what, of course, when you divide an integer by a positive integer, it could divide, let's say evenly, and then we come up with the result of this division, actually just a single number. However, if it doesn't divide evenly, okay, then we end up with a remainder, right? So suppose I have number 13. I want to take both integers actually to divide are positive for the time being. And then I want to divide, this is by 5. We know that division is actually the process of repeated subtraction. What does this mean? This means we need to find how many 5s basically are in 13. So if I start with 13, then subtract 1 5, we come up with 8. Then if I subtract from 8 another 5, I come up with a 3. Then if I subtract 5 from 3, I come up with a negative number. So the process ends when we cannot actually subtract any more 5s, in this case a 5, without going actually to the negative. So we express this by we subtracted 2 5s. Then we say that actually 13 over 5, which we know that is equal to 2. How many times? Actually, I subtracted the 5, and then the 3 over 5. So we could express 13 over 5, which is 2 plus this, which we write it as a mixed fraction 2 and 3/5, right? Well, we would like to express this as an equation in Z. As an equation in Z. Means everything integers, we don't have fractions in here, if you will. Then we could arrive at this by multiplying the two sides of this equation by 5. So then we can express 13 as 2 times 5 plus a 3. So the 13 and the 5 are the numbers that we are dividing, sort of, and we refer to the number 2 in here as the quotient, and we refer to the number here as a remainder. All right, so the division algorithm is basically saying that if you are given two integers, an a and a b, that is positive, that we're going to start with, then we can find two integers, in this case the 2 and the 3, and these are unique. And we cannot find any others to express 13 in this form. All right? So there exists a quotient and the remainder, which satisfy the remainder certain properties. So let's actually state the division algorithm in general. Here it is. So this is theorem, and this theorem is actually 2.1. And we refer to this as the division algorithm. State this, let A and B be integers such that B is bigger than 0. All right, then there exists unique integers Q and R called the quotient and remainder. Since they are unique, so we use the word the, okay, the quotient and the remainder. Such, and, okay, so there exists these such that A is equal Q multiplied by B plus R, where R is bigger than or equal to 0, but strictly less than B. All right. In fact, we sort of, for the proof, we're going to be using, need to use the will ordering principle. All right, so this gives us a clue where to go from here. So to use the will ordering principle, we need to come up with a non-empty set of non-negative integers and then find, then by the will ordering principle, it tells us that this set is going to have a, a least element. So basically, another way to think about this is we wanted to look at a set like this. So we're going to consider, which is this what we said about this repeated subtraction. So we're going to consider the set S, which consists of A and subtracting from it multiples of B, okay, KB. I cannot say Q because we need to put our hand on the Q. We don't have the Q yet. Such that K is equal 0 plus minus 1 plus minus 2 and so on. Now, this set is going to contain positive integers, negative integers, and 0. All right? So we need to take a subset of this that contains elements where this is actually non-negative. Okay? So we're going to define another set. Or subset of this. Basically, we're going to take a subset of this. And then let S positive here, okay, to be the subset of S whose elements are non-negative. So in other words, the S, this, it consists of those elements A minus KB, such that the A minus KB is bigger than or equal to 0, and the K is equal, again, 0 plus minus 1, and so on. All right. The first thing I want to claim that this set, all right, it actually is not empty. All right. So this is the first thing. We know it consists of. So this is as a subset that we were defining it. This one is a subset of the natural number together with 0. All right. All right, so first we have a claim that S plus is not empty. We're going to consider two cases. Case 1, if A is negative, and case 2, A is bigger than or equal to 0, positive or non-negative, basically. So if A is less than 0, then let's look at this number. Then A minus AB, I can take K to be equal A. This is equal A times 1 minus B. Now I know that A is negative, and the B, from the way we took B, remember B is bigger than 0. This means that B is bigger than or equal to 1. Okay, so the smallest value B could have is 1. And from this, we conclude that if you subtract B from here, you get 1 minus B. So 1 minus B is also negative. So you have actually a negative times a negative, all right? And this one is going to be actually positive. So this is bigger than or equal to 0. Let me put in here, actually, say non-negative. Could be equal to 0 if B is equal to 1, okay? So at the end, we get this is bigger than or equal to 0. All right? And this is the way we're defining this are those elements which make this bigger than or equal to 0. Case 2, if A is bigger than or equal to 0, then A, it's going to equal to A minus 0 times B. All right? And this belongs to, of course, S plus. In here, I should say this one, this implies actually A minus AB is in S plus. So in both cases, we have at least one element in S plus. All right, now we're going to apply the will ordering principle. okay, by the will ordering principle, by the will ordering principle implies that S star has a least or smallest L. We're going to call it R. By the definition of S star, R is going to equal A minus some integer K times B. We're going to call this integer Q. All right? So in other words, here for some K, which is equal to Q, and this is an integer. So we're going to call it a Q. So now we have found, in some sense, the R, okay, and the Q, but we need to show that it does satisfy the property on that inequality on the R. Again, since R is in S plus, this implies R is bigger than or equal to 0. So this is one part of the inequality. The next thing we want to need to show R is actually smaller than B. All right, to do this, we're going to consider the following. So we need to consider R minus P. Okay, so we're going to consider this, R minus B. By definition of R, remember it's equal A minus Q, B minus B. Let me rearrange this so that I can write it as actually A minus. Then I'm going to take these together and I can factor a B out of it. Then we have Q plus 1. All right. Now, this is an element, at least I know it is in S. All right. Because it has the form of the elements of S. And one other thing, we also have R minus B is smaller than R. Why is this? Because since B is positive, okay, so bigger than 0. So if you subtract from an integer, actually, remember R is also bigger than or equal to 0, a positive number, you actually reduce its value. All right? Now, if this R minus B is bigger than or equal to 0, equivalently means R minus B is NS plus, we have a contradiction. We have a contradiction because R is the least element in S plus. But here we have we have R minus B is actually smaller than R. So this is not true. What does this mean? This means no, we cannot have R minus B to be actually bigger than or equal to 0. So this implies, yes, forces R minus B to be less than 0. And from this, we obtain that R is smaller than B. And we are done. As far the existence. So we have shown the existence of Q and R such that A is equal QB plus R and the R bigger than or equal to 0 less than B. Now we need to prove uniqueness. Okay? All right, let's move on to prove the uniqueness. By the way, sometimes my proofs slightly differ from the way the book presents the proofs. You like the way the book does the proofs is fine. You like the way I write the proofs is fine. Doesn't make any difference. All these are good and correct. Okay? So to prove the uniqueness of Q and R. So to do this, let's assume we have two ways we could get Q and R and another Q and R. Okay, so we can assume that A is equal to Q, B plus R, and A is equal Q prime, B plus R prime, where we have the R here is between 0 and B, the same thing in there. And I need to show, no, we must have the Q must equal to Q prime and the R must equal R prime. Well, let's assume by contradiction. I'm going to assume the Q's. Assume that Q does not equal Q prime. So this implies either the Q is smaller than the Q prime, or the Q is bigger than the Q prime. Because by the symmetry of the argument, we're going to take one of these cases and see that would actually lead to a contradiction. Okay? So that's why we're proving something will go wrong. So let's assume that the Q is less than the Q prime. This implies if I add 1 to the Q, it might actually become equal to, okay? But it's not going to get bigger than. It's going to be less than or equal to Q prime. All right? Now let's look at this R. Remember, we have the R actually is equal to, let me see if this is, yeah, let me write this one as A minus QB. And I'm going to replace the Q by Q plus 1, okay? So I can say this is actually is less than or equal to A minus, so I'm going to put in here the Q prime Alright, so I am replacing the Q by, actually this is a Q. Alright, so I am subtracting from A here, alright, QB, alright, and I'm subtracting a bigger number, okay, from A, and this would make